This lecture is about translations and rotations, and this will be the main topic for the rest of the course. First, a translation will be a function which takes the point xy to the point x plus a, y plus b for some a and b. So again, a translation is just going to replace xy then with x plus a and y plus b, and it's going to do this for every point in the plane. So if we imagine the vector AB being as drawn down here, and we want to know what this translation is doing to points, it's basically going to move all the points in the direction of the vector and the same length as the vector. So it would have this effect. So a translation moves points in a certain direction, a certain amount. We're going to be using this matrix when we talk about translations, and it has the nice property that if I multiply this matrix by xy1 on the right, it's just going to give me the result of the translation x plus a, y plus b1. And we can see that with a direct computation. If I take the translation matrix and multiply by xy1, and to remind you how that's done, we take this row and we're basically dotting it with this column, thinking of them as vectors. So we're taking 1 times x plus 0 times y plus a times 1. And that'll give you x plus a. And then we multiply the second row with the column. And this is going to be, again, a dot product. We're going to have 0 times x, 1 times y, and b times 1. And so that's going to give us y plus b. And then finally, we take the third row and dot it with the column, and we get 0 times x, 0 times y, and 1 times 1. So adding those, we just get 1. So we can think of this matrix then as being the translation. We just take this matrix, multiply it by x, y1, and we'll get the translation x plus a, y plus b, and with an extra 1 here. For rotations, we want a point that we're rotating around. So this is the x1, y1 here. And we want to take points in the plane, all the points in the plane, and rotate them about x1, y1 by the angle phi. So we're going to turn them around this point with an angle of phi. So the results of doing that rotation with these points would be that. So that's how rotations work. And we have a matrix that represents the rotation. And it's a little bit messy. But notice you're given the x1 and y1 and the phi, so you want the point you're rotating about and the angle you're rotating about for this rotation. And that's what's involved in this matrix here. It's using that information to construct this matrix. And we want this matrix to have the property that if I take xy1 and multiply on the right with this matrix, that we end up with the rotation, whatever it is, wherever we're rotating to. But part of the difficulty here in verifying this is that what are we rotating to? It's not like something simple like you have xy and you're translating by ab, then you're just going to get x plus a, y plus b. Instead, we're having something else here and it's not clear what that is. So we need to figure out what a rotation about some point x1, y1 by an angle of phi does to xy. And once we do that, we can see that multiplying by this matrix does the same thing. To clarify, rotations for us will always be counterclockwise. So notice I turned this way with the points. I went by phi this way. So we're always going to go counterclockwise when we're talking about rotations. That'll be a rotation. So again, what we're interested in showing is that when I take this matrix that I have up here and multiply by x, y1, we get x prime, y prime 1, where x prime and y prime are the results of a rotation of xy about the point x1, y1 by an angle of phi. But again, in order to do this, we need to know what's going on with x prime and y prime. What are x prime and y prime here? What is the result of this rotation? So what we're going to do is do this in two cases. The first case, we're going to consider the x1, y1 just to be the origin, just to be 0, 0. So this is 0, 0, and we're going to go ahead and find out what x prime and y prime have to be. So I've made this 0, 0. And I'm imagining now that this is not the matrix we were talking about, but is the function that rotates the point xy about 0, 0, the origin, by an angle of phi. So the picture looks like this. I'm rotating around the origin by the angle of phi, and I'm looking at xy, and it's going to go to x prime, y prime. I want some idea of what this x prime, y prime is. It should have something to do with this phi, as well as x and y. So what we're going to do to make this come out nicely is we're going to rewrite x and y, and x prime and y prime in terms of polar coordinates. So let me begin by rewriting xy in terms of polar coordinates. So I have x is r cosine of theta and y is r sine theta. And to remind you, r is the distance from xy to the origin, so it's that distance. And theta here is the angle with the positive x-axis, so it's this angle down here between this line and the x-axis. So now we look at x prime, y prime. Notice that the distance to the origin is the same because we're just rotating about this origin by an angle of phi. It's not going to change the distance from the origin. This is still going to be r as far as the distance from the origin goes. The angle, on the other hand, well, this is phi here, and this is theta. So the angle from the positive x-axis is going to be theta plus phi there. So the polar coordinates for x prime, y prime are going to be r, again, because this is r, and then cosine of theta plus phi, because this is theta plus phi, and r sine of theta plus phi. What I'm interested in is looking at x prime and y prime here. I don't like the way it's written right now because I want an answer that just depends on x, y, and phi here. So what I'm going to do is look at x prime being r cosine of theta plus phi, and y prime as being r sine of theta plus phi, and rewrite those. So x prime again is r cosine of theta plus phi. And how should we rewrite that? Well, you see cosine of a sum of two angles, well, that uses a formula for that, right? So the formula, to remind you, is you take the cosine of each of these, cosine of theta, cosine of phi, and you subtract, when you have a plus sign here, the product of the sines of theta and phi. So it looks like this. We have cosine of theta, cosine phi, minus sine theta, sine phi. But now you can see when I multiply it through by r, I have r cosine theta here that I can replace with x, because x was r cosine of theta. So this will be x times cosine of phi. And I also have an r sine theta, so an r sine theta, which is y. So this will be minus y sine phi. So writing that down, I have again r cosine theta is x, cosine of phi. I have a minus r sine theta, which is y, and then sine phi. Now this looks good because now when I begin with the point xy and the angle phi here, I can say what x prime is just based on that knowledge of what x, y, and phi are. So I want something like that also for y prime, and we do the almost exact same thing here. I have y prime is r sine of theta plus phi, and then I'm going to use the formula for sine of the sum of two angles. So I get sine of theta cosine of phi, and then plus in this case, sine phi cosine theta might be the way you remember it, but I'm putting the cosine there and the sine phi there. With the intent of noticing that r sine theta, again, is y, and r times cosine of theta is the x. So I'm going to have y cosine of phi here plus x sine of phi. So y cosine of phi plus x sine phi. And again, that looks like what we want. It's an expression in terms of x, y, and phi. So I have these two expressions in terms of x, y, and phi for x prime and y prime. And that tells me then, given the x, y, and the phi here, what the rotation of x, y about the origin by the angle phi is. It's x prime, y prime, where this is x prime and this is y prime. Let me now look at case 2, where x1, y1 is not the origin. Notice I replace this now with x1, y1 here as well, but the origin is here, and now I have some x1, y1 someplace else, and I'm rotating xy to get x prime, y prime again. Now I'd like an expression for x prime, y prime that's in terms of xy, the angle phi, but also the point I'm rotating around. These expressions are not correct. This is what I had when we were rotating about the origin. The theta here was the angle from the positive x-axis. That's no longer the case. And the r here has also changed. But what we want to do is shift this picture so that it is at around the origin, where this becomes the origin. So we're going to do a translation that takes this to the origin for that whole angle there. So I've translated this down to here. So what happens here, I've subtracted x1 from x value here and y1 from the y value here to make this the origin. If I want to translate by the same amount, I got to do the same thing with each of these. So I want to translate this to here. I'm going to subtract x1 like I did here and subtract y1 from y. And this point is going to become x minus x1 because I subtract x1 and y minus y1 because I subtract y1. Okay, so that's what happens if I translate this to the origin. I have to subtract x1 and y1, so I need to do these with all of them. I subtract x1 and y1 from xy, and I get this. And similarly here, x prime y prime is going to become x prime minus x1, y prime minus y1, because I want to translate that by the same amount too. So this is really the same picture down here that we have up here, just translated. And now to make use of what we did before, I'm going to go ahead and look at the r and theta for this. So really, this expression I want to put down here. So let's do that. This is now going to be r cosine of theta, r sine theta, this being the angle theta, and r being the distance from here to here. So I've rewritten this as r cosine theta, r sine theta, and as we know from what we did in case 1, then this point that it gets translated to is this expression now. So this point, x prime minus x1, y prime minus y1, will go to r cosine of theta plus phi, r sine of theta plus phi. Again, because this is still r, and this is theta plus phi. So what we found out in case 1 was that the x prime was x cosine phi minus y sine phi. Well, what was this x and y? The x and y came from here, and the x prime y prime came from this point here. So I need to replace x and y here with x minus x1, y minus y1, because that's are the coordinates here now instead of x and y. So this will become x minus x1. This will become y minus y1. This will be an x minus x1. And this will be a y minus y1. And what about x prime and y prime? Well, that corresponds to this point, which is now x prime minus x1. So this will be x prime minus x1. And the y coordinate will be y prime minus y1 here. So I want to make all those changes. make some room here and just write down what those changes are. So x prime again gets replaced with x prime minus x1. X and y here get replaced with x minus x1 and y minus y1. And then I did the same thing with the y here. The y prime gets replaced with y prime minus y1. And the x and y get replaced with x gets replaced with x minus x1. And the y gets replaced with y minus y1. So this is an expression then that we have for x prime and y prime. Let's go ahead and put this minus x1 and this minus y1 on the other side just by adding x1 to both sides of the first equation and y1 to both sides of the second equation. So now we have what we want. We have an expression for x prime and y prime that only involves the given information, the point x1, y1 we're rotating around, the angle phi we're rotating by, and then the point xy we're interested in rotating. So these expressions are what we want for x prime and y prime. So now we know what x prime and y prime should be here if we rotate xy about the point x1, y1 by the angle phi. So the next question is this really the same thing as multiplying xy1 by this matrix up here? So let's just look at that. I put the matrix down here, and I put xy1 here, and we want to look what happens when I do that multiplication. So the cosine of phi gets multiplied by x, the minus sine phi gets multiplied by y, and this expression gets multiplied by 1. This should be the same value when I do that, when I add those, as x prime. We want the product of this and the first row to equal x prime. So let's check. We have x again times cosine of phi. We have an x times cosine of phi here. So that x cosine of phi comes from cosine phi here times x. We have a minus sine phi times y. That corresponds to this minus y times sine of phi. So minus y times sine of phi. And now we have this 1 times this. Notice the x1 times 1 is right here. So we have x1 at the end of our expression for x prime. The x1 times minus cosine of phi is right here. We have minus x1 cosine of phi. And the y1 sine phi is the same thing as two negatives here, y1 sine phi. So the y1 sine phi is coming from this product and from here. So it's the case then that if I take this vector here and dot it with this vector, I am going to get x prime like we want. So that's given me that part of this equation with this matrix here. Let's look at the next row and dot that with xy1 and see if we get y prime. You can see we're going to get x times sine of phi. We have an x times sine phi. We're going to get cosine of phi times y. In y prime, we see a y times cosine of phi. And then we want 1 times this. So again, the y1 times 1 is at the end here for y prime. We have a minus x1 sine phi coming from here, minus x1 sine phi. And we have a y1 times minus cosine phi coming from here, the minus y1 cosine of phi. So when I take this vector and dot it with this vector, I do get y prime. So I am getting that, and that comes out just like we want it. The last thing to check is if we have a 1 there. Here we're just multiplying 0 times x, adding 0 times y, and adding 1 times 1, and that's just going to be 1 like we want. So this extra 1 coordinate's not doing much. We're always going to have 0, 0, 1 here, dotted with this being 1. But what it's really doing is helping the rest of the product. I need x times this, y times this, and 1 times this to give me what x prime is. And similarly for y prime. So we've shown then that multiplying this matrix by xy1 gives us the x prime y prime 1. And so the matrix is doing what we want. It's doing the rotation for us. If I take that rotation matrix and multiply by xy1, I'll get x prime y prime 1. And I can find out what the rotation of xy is then about the point x1, y1 by the angle phi. And to summarize, then we have these translations and rotation matrices. The translation matrix looks like this. The translation matrix times xy1 will give us x plus a, y plus b1, and the x plus a, y plus b is what we get after we translate by xy. And we have this messy looking rotation matrix, but it does what we want. If I take that matrix and multiply by xy1, it'll give me x prime y prime 1, where x prime y prime really is the rotation of xy about the point x1, y1 by an angle of phi. So that finishes this lecture.